In this video, we want to give two more examples of the power of polymorphism. These are very simplistic examples, but it does demonstrate how polymorphism works. So the first thing we have here is an employee class. This will serve as the base class. So notice for this employee class, we simply have a constructor and a get bonus function. We have a protected section for the ID and the sales for an employee. Again, this serves as the base class. Then we have, derived from that base class employee, an intern class, an entry class, and a manager class. In the intern class, notice the constructor simply calls on the base class constructor, that preemptive call right there, to fill the base class part of the object with the what's going to be the sales and the ID right there. All right, the entry and the manager class all do the same thing. You will notice that the entry class has also an additional data member called rate that does not appear in the employee class. So in the intern class, the rate is 10%. Entry, it's 20%. And in the manager class, it's 30%. We'll see how that factors in just a second. So if we look at the client program here, what we're going to do is create a base class pointer employee and then instantiate three objects, an intern, an entry, and a manager. And then we're going to take that base class pointer and point it to each one of these objects one at a time. When we point it to that object and use the base class pointer to call on the get bonus function, because that's a base class pointer, it should simply call on the base class get bonus function, which simply returns 0. So if we look at this illustration here, we see that when the base class pointer points at each one of these objects, it will only see the base class part of it and should just print the bonus out as 0. Let's run the program and see what happens. So if we see here, Ivan, Emily, and Mickey all have bonuses of 0 because the base class pointer could not see that these were derived objects. All the base class pointer could see was that the object was of type employee. So now we take the same code and we look at it with now virtual get bonus functions. So by simply prefixing this with the word virtual, we're telling the computer to not resolve that function call until the program executes. Again, we call this late binding or dynamic binding. So now instead of calling on the get bonus function for the employee class, the base class pointer should see the get bonus functions for each respective class. So it's going to see the get bonus for intern, which we made that 10% of 100. It's going to see the one for entry and manager, which again, we changed the values here to illustrate the difference. So they all get $100 in sales, but then when we calculate the bonus, we should have a different bonus for each one. Let's see this program run. And now we see that Ivan has $110 because he got a certain percentage of his sales and a $100 bonus. Emily received $220 because she got 20% of her sales plus a $200 bonus, and so on and so on. What we really see here is that the base class pointer pointing to each one of these derived objects can now see the get bonus function from the derived class. So again, if we go back to this illustration, now when the base class pointer points to the intern, it does not see the base class, or I should say it does not bind to the base class get bonus. In fact, it binds to the derived class get bonus. I had to abbreviate that because of space, but this is the power of polymorphism. While this program is running, the base class pointer can see that object as a derived object. It changes into an entry. It changes into a manager on the fly. So let's take a look at our next example. In this example, we're going to have a container class called a shape list. The shape list class is going to consist of a linked list of shapes. So we're going to have a base class called shape, and then that base class will be used to derive a circle class, a rectangle class, and in this case right here, we're going to use the rectangle class to derive a square class. So the square is going to be a rectangle, which is a shape. So 2 levels of inheritance here. Okay, we'll notice that in this shape list class, we'll have this first shape pointer that will be of type shape, the base class. That will allow it to point to the shape nodes. And each shape node will have in it a pointer to the next shape. So let's look at the code. In the code here, I see I have instantiated a shape list object called SL shape list, and I have a for loop that's simply going to go through and add shapes to this list. Now I just have a for loop going from 0 to 3, so it's going to add 3 shapes to the list. Once we add those shapes to the list, we're then going to call on a display function that will simply display the entire list. So if we get into the actual .h file, the header file, we see that there's a base class called shape, and it is making shape list a friend so that it has access to the next pointer. We also have a destructor in here and a print function, print shape name. Now notice for the base class, we're simply going to just print the word shape. And also notice that this is a public section and this is a protected section, setting it up for inheritance. In the next class, circle class, we see that circle inherits publicly the shape, which means it inherits all the public and protected section. Now the circle class is a simple class just for this illustration. It simply has a print shape name function, so it's redefining the function from the base class. It has the same signature, only this print shape name will print that it's a circle. If we go down and look at the rectangle class inherits from shape also. It has the same shape name function and it prints rectangle. Now look closely at the square class. The square class is actually a derived class that's deriving from the rectangle. So the rectangle is the base class of the square. But remember, the rectangle is a shape. So the square is a rectangle, which is a shape. So that's 2 levels of inheritance there. And again, we just have this one simple function in here to print the shape name. It will print square. All right, so all the real stuff is going on in the implementation file with shape list. So let's look at the shape list class definition first. There's a simple constructor here that simply sets the first pointer to null. And then there's a destructor, an add shape, and display methods for this class. Now the class has a head pointer called first shape. That head pointer is going to point to the list of shapes. Remember, the list looks like this, and it's going to point to a bunch of shapes on the list. All right, so let's now look into the implementation of this. In the implementation file, we simply have the implementation for the shape list class. All of the implementation for the circle, square, and rectangle are inline. And remember, we said inline functions are good because they actually insert the code in the place of the call for the function. So there is no call, and the code executes more efficiently or faster. So going back to the implementation for the shape list, we have a destructor here. This should look very familiar. This function simply will destroy the entire list once the object is about to go out of scope. So we'll see that happen when we run this code. But again, very familiar code. We've seen it before. In the add shape function, it simply takes an integer, and depending on that integer, if it's a 0, 1, or 2, it instantiates an object based on that number. So we have a shape pointer, which is a temp pointer that will point to that particular shape. Now remember, the base class pointer can point to that derived class object, but it only sees the base class part of it. It's okay because all we want to do is connect it to the list. So depending on what that integer is, we instantiate a dynamic circle, rectangle, or square, and then this code should look familiar right here. We're simply going to add that new shape to the top of the list. Okay? Again, familiar code. Once we add that new shape to the top of the list, remember in the client program, we're simply calling that over and over, sending in 0, 1, 2, and 3, which means we're going to create a circle, a rectangle, and a square, very similar to what we have here in this diagram. A circle, a rectangle, and a square. Okay? Now, once we populate that list, we're then simply going to print it out. Notice, again, the temp pointer is of type shape. We started at the head of the list, and then we traversed the list, printing out the shapes. But here we're calling on print shape name with a base class pointer. If you remember, print shape name is a function that's been redefined from the base class into all of the derived classes. So each one of them has a print shape name. So if you want to envision this, there's a print shape name here and a print shape name here in the derived part of it. The derived part prints the circle, the base part of it prints the shape. Now, from what we've learned earlier though, since these functions are just redefined in this manner right here, when I run this program and go through this print function right here, the temp pointer is only going to see the base class part of it. So let's run it and see what happens. And as we run it and go down the list to print each shape on the list, notice that the output is simply shape, shape, shape. It doesn't see it as a circle, a rectangle, and a square. It only sees the base class part of it. Now, I've added a press any key to continue right here to stop in the main program. But notice when I hit this, it then goes into the destructor. So the destructor is doing its job, getting rid of that dynamic memory before the program terminates. So again, let me make sure you understand what's going on here. I have a system pause here that stopped me the first time. But after I hit enter to cancel that system pause, before I got to return 0, I went into this destructor here that got rid of the list, printed this message, and then I had another system pause to stop that process so you can see that the destructor did do its job. Again, let me run it again. Again, there's the output for the program. I hit continue, and now it says the destructor did its job, and that's that second system pause, and now it's done. Okay, great example. The only problem is when we go down this linked list using temp to point at each one of these objects, we would like it to not see just the base class part, but actually see the derived class part. Now, in the other demonstration, we talked about that being late binding or dynamic binding. That happens during execution, and if we look at this code again, during execution, as this display function is running, when temp points at a node, we want print shape name to be bound to its function dynamically as the code is executing. So when it's pointing to a circle, we want it to be bound to the circle print shape name function and not the shape print name function. So we actually want this thing to resolve itself while the program is executing. How do we do that? We simply prefix the function prototype with the word virtual. Again, by putting virtual in front of that, we're telling the compiler, don't resolve that binding during compile time. Remember, when it's resolved during compile time, we call that static binding or early binding. Usually when we see the dot notation, we know it's going to be static binding or early binding. But when we see the pointer notation, if we have a virtual function, we can wait and do the binding. When I say binding, I mean figuring out which function we should call, the base class or the derived class. We can figure out that binding during execution time while the program is running. So a couple of things to note here. By putting virtual in front of this base class function, by default, all of the derived class functions automatically become virtual. But again, it's a good idea to write the word or enter virtual in front of each one of the prototypes just to let someone know that this function is going to be dynamically bound, have dynamic binding. And the last thing is, whenever you create a virtual function within a class, you must also make the destructor virtual. Why do we do that? Again, if that pointer is a base class pointer, when we start to delete or get rid of this thing, if the derived part of it has any housekeeping or cleaning that it needs to do, we need to let that virtual function go out, that the virtual destructor go out and clean up the derived class part of it too. So we make this destructor virtual just in case the derived class also has dynamic memory that needs to be deallocated. So now that we put the word virtual in front of all of these functions, let's see how this executes now. And as you see here, now that we have virtual functions, the binding happened late during execution. And when we got to this statement right here, where we started printing out these shape names, the program realized that that was a square and it printed the square. Remember, the square was added last, and that was a rectangle and it printed rectangle and circle. So it printed these, so it printed the derived class print name function instead of the base class print name function. This is called polymorphism. And we also call this function overriding. Function overriding is when the base class pointer realizes that it's not supposed to call on its own function, but override that call and call on the derived class function. So at that point, the function is overridden, or it's an override, and it goes to the derived class print shape name function.